So let's start our analysis of LRC circuits by trying to find an expression for the charge on the capacitor plates as a function of time. This is a sheet you probably have in your notes. I've just redrawn it to neaten it up a bit and add a couple of words. So we're going to begin our circuit analysis with the switch in position A. So the switch is initially going to be up here. What that means is that the battery is going to fully charge the capacitor. So our circuit starts at switch A. Battery fully charges capacitor. So one plate has charge plus Q, one plate has charge minus Q. So this is the only part of the circuit through which current can flow. And we know that the charge on the capacitor plate is going to be the potential of the battery times the capacitance. At time t equals 0, we're going to flip the switch down to position B. So at t equals 0, we'll flip that switch. So then what happens is the battery is no longer connected, and I forgot to put a resistor in my circuit. I'm belatedly going to put that resistor in. Hopefully that's not too messy. All right. So now when we flip the switch down to point B, we have a fully charged capacitor, an inductor which is going to resist current flow, and a resistor which is going to dissipate some energy. The current will begin to flow, although this will resist it. Ultimately it will start to flow. So at t equals 0, we flip the switch to position B. Current will begin to flow at some point. We'll use our same tool for circuit analysis. We'll write Kirchhoff's potential law, and we'll use that to find the charge on the capacitor. So for Kirchhoff's potential law, let's identify a loop and let's identify the current. So the current is going to flow. The positive charge will leave the capacitor plate. So this is what the current flow will look like. Let's draw a loop. Let's take our loop coming around this way. Let's write Kirchhoff's potential law for that loop. So the change in potential across the capacitor plus the change in potential across the inductor plus the change in potential across the resistor all has to sum up to give 0. That's Kirchhoff's potential law. The potential across the capacitor is the charge on the plate divided by the capacitance C. The potential for the inductor is minus the inductance times the change in current with respect to time. And the change in potential of the resistor is, it's a drop, so we've got minus I times R according to Ohm's law. Looks like we have two unknowns, but we do have a link between charge and current. We know that in general, current is the flow of charge over time. For this question specifically, dq, this general dq, is negative. So charge will start to flow and the inductor will start to charge up when charge leaves the capacitor plate, so we get a negative. And we've identified the charge on the plate as a capital Q, so we'll use capital Q here. So the current flow is charge Q leaving the capacitor plate. Okay, we can fill that in for our current in our Kirchhoff's law expression. So Q over C minus L times d by dt of minus dq by dt. Got to be really careful with all the signs here. Minus a negative dq by dt times R equals 0. This is a solvable expression. Let's just neaten it up a tiny bit. So Q over C, minus times a minus is plus, L, d by dt is the second derivative of charge with respect to time. Negative times a negative is positive, so we've got plus R times dq dt. Okay, so let's divide the entire expression through by the inductance L. Q over LC plus D2Q dt2 plus R over L dq dt. That equals 0. Now I'm just going to arrange them in order of the terms. That's a more traditional way to write it down. So the second derivative of charge with respect to time plus r over L times the derivative of charge with respect to time plus q over LC equals 0. I'm not going to go through the math approach to solve this. I'm just going to present you with the solution. So this expression has a general solution of q as a function of time is equal to the maximum q, so the maximum charge on the capacitor plates, times e to the minus r over 2L times t times the cosine of 1 over LC minus r squared over 4 times L squared times t. And this part is under a square root. Okay, t is not under a square root. Just make sure that's clear. Plus some constant phi. Okay, in this expression, the constants are Q naught, that's the maximum charge, R, that's the resistance, L, that's the inductance, and phi naught, that's the phase constant. So if we wanted to make a plot of the charge as a function of time, we would see that it would die off with a slightly changing frequency. This term corresponds to the frequency of the oscillation. So if we wanted to make a plot, we would put Q on our vertical, time T on our horizontal. I'm going to cheat and draw my envelope first, just because I don't draw super well. So you'd have an envelope that looks something like this. So you get your exponential die-off. That's this part right here. This tells you how the amplitude dies off. And inside, this tells us that we have an oscillation. So your charge as a function of time looks a little bit like this. This outer envelope is the amplitude of the oscillation, Q naught e to the minus r over 2L times t. Okay, so this is the die-off part, this is the oscillation part. Something we might ask here is what happens in a circuit where R goes to 0? That's a fair enough question to ask. So what if R equals 0? You might anticipate that we should just recover the expression we had for an LC circuit. So if R is equal to 0, then our charge as a function of time is Q naught e to the 0 times t over 2L, negative I suppose, times cosine 1 over LC minus 0 squared over 4L squared, square root times t plus phi naught. Put brackets around. So for our zeros, let's deal with those guys. You get Q of t equals Q naught. E to the 0 is just 1. Cosine square root 1 over LC times t plus phi. So this indeed is the LC circuit expression. So where the angular frequency is 1 over square root of LC. So we get Q of t equals Q naught times cosine omega t plus some phase constant. So we do recover that circuit. Recover LC circuit equation. So that's a good thing. We always hope to recover it. So this is what we have if in LC, our angular frequency is the square root of 1 over LC. In this expression, omega equals 1 over LC minus R squared over 4L squared. This is the angular frequency of an RLC circuit. So let's see, what's one last thing we'll mention before we clue this part up? If you have an RLC circuit and you apply some sort of sinusoidal force with the correct angular frequency, you'll get a resonance in that circuit. You'll get the maximum response. That's what leads to an AC circuit, so an alternating current circuit where it goes back and forth with the maximum response.